Alright, so warm-up problem for you to work on while I take the attendance. Before I forget, let me remind you that tomorrow you have a formative in the Resource Center that you should take. Okay? So definitely want to do that formative tomorrow. Alright? So I've got a focus at -3, 4, and then I've got a directrix at x equals -6, or excuse me, y equals -6. That to me says that there is a distance between those two of 10. 4 above and 6 below makes a distance of 10. So 5 down would be my vertex. So my vertex would be at the point -3, -1 in order to make this be a distance of 5 and this be a distance of 5. So that vertex puts it there. That makes this an up-down parabola, correct? Okay. So an up-down parabola would be x minus h quantity squared equals positive 4p times the quantity y minus k. H is -3, k is -1, p is, what's p? 5. Okay, so I have enough to make my equation, and my equation is x plus 3 quantity squared equals 20 times y plus 1. Yes? Okay. Fantastic. Okay. Today we're going to switch gears, and we are going to go to the third of 4 conic sections. And the third conic section that we are going to go to is an ellipse. Okay. Now, the nice thing about an ellipse is that there's a little bit of, like, I don't like curved line in this definition of it, but I like the interactive website that they give me. Okay? So an ellipse is a curve. I'm just going to call it a curve instead of a curved line. An ellipse is a curve that forms a closed loop. Okay? Another example of a closed loop, a circle. Okay? So an ellipse is a closed loop where the sum of the distances from 2 points that are called the foci, focus is singular, foci is plural. So since there's 2 of them, now it's called foci. To every point on the curve is constant. Okay? So here's where the interactiveness of this website is where I like it. Okay? So so here's my first focus. Here's my second focus. In an ellipse, there's 2 foci. what this definition is saying is that the distance from the first focus to this point right here, plus the distance from that point to the second focus, is always going to be the same, no matter where I go. So here is A, the distance from the first focus to the point. Here is distance B, the distance from the second focus to the point. And anywhere that I go on that ellipse, that distance is constant. Okay? And that distance is equal to the length of what is called the major axes. Okay? So that distance is always constant for any point that I go. Sometimes distance A is longer than distance B. Sometimes distance B is longer than distance A. But the sum of the two is always constant. That's the technical term to describe an ellipse. Okay? Another way to describe an ellipse is you take a circle and you grab onto two sides, left and right, or top and bottom, and you pull. Okay? You stretch it out horizontally, or you stretch it out vertically. Okay? Or conversely, you could squeeze it horizontally and vertically, okay? And then it would stretch out the opposite way. Okay? That's another way of describing an ellipse. Okay? Okay? So my goal in the next half hour is to give you an equation of an ellipse and have you graph it on your piece of graph paper. Okay, that's my goal in the next half hour. Actually, to do two of those. Okay? I think we can do it. Okay? So first off, we have to start with the equation of an ellipse. And here is the equation of the ellipse. The quantity x minus h squared divided by a squared plus the quantity y minus k squared divided by b squared equals 1. That is the equation for any and all ellipsi, if you will, okay, that we can make this entire week. Side note, we are not going to have a quiz this week, Thursday, because of last week, Thursday's snow day. Okay? So I took that quiz out, and that puts us back on the same schedule for finishing the year. Okay? There is one condition to this formula, or to this equation of an ellipse. And that condition is that A cannot equal B. Anybody know why? They have to be different.
Isn't it what you were just showing us?
What do you mean?
Like you were moving them so they can never really be equal. I don't know.
This A and this B is different than that A and that B that I was showing before. Anybody know why? They got to be different? If they're equal, it's a circle. If they're equal, it's a circle. They have to be different in order for it to be an ellipse. An ellipse mirrors a circle, yes, but it's got more parts to it. So it's got more things to do to it because it's not. It's a much, or a more advanced version. Okay? So that's the equation that we're going to use this week and for the rest of this chapter, because that's going to be helping us to graph ellipses. Now, a little side note for you. Ellipses in real life. Okay? They're all over. Okay? Anybody give me an example of an ellipse in real life that you could think of? Maybe from a science class. None? Anybody take earth science? Yeah? Study planetary motion in earth science? Yeah? Comets? Stars? All that stuff? Or is that more astronomy? You do that in earth science? Anybody take chemistry? Yeah? What are you studying in chemistry? Or what have you studied?
Reduction.
What?
I'm studying oxidation and reduction.
Oxidation and reduction. So, how can I tell the difference between elements? Or even better, how can I tell the difference between carbon dioxide and carbon monoxide? Charges. They have different molecules, right? Okay. What do I know about a molecule? Or what's a molecule made of? What's anything really made up of? Atoms. What are atoms made up of? Protons, neutrons, and electrons, right? Anybody give me an example of elliptical things in life? I just gave you 3 of them. None? We'll go left to right, top to bottom. Okay? Top left. The movement of a comet around a celestial object is in elliptical fashion. Can I borrow this for 2 seconds? Okay? If I were to take a water bottle and I see that I got some water in it, okay, and I draw around in space, if I were to draw around the edge of the top here and then take this away, I'd have a circle right here, right? If I tip it to the side, now if I look straight down on it, that's an ellipse. Some buildings have elliptical roofs or elliptical shapes. Smack dab in the middle, protons, electrons, and what was the other one? Neutrons?
Protons and neutrons and the electrons
Go around it. So the electrons go around a proton and a neutron in an elliptical orbit. Okay. Some games here in the middle on the bottom, some games have elliptical. This is a billiards game. Okay. Pool is what we know, where you shoot the ball into the pockets. Okay. 8-ball corner pocket kind of a thing. That's pool. Okay. Billiards is a more geometric game where you got to hit certain sides before your ball touches things and all. It's actually pretty cool because it's very highly mathematical. Okay. The bottom 2 on the outsides though are the cool ones. Okay. The one on the right is I think it's St. Paul's Cathedral in Europe. Its shape is elliptical. Okay. They made it in the elliptical shape. Okay. The one on the left is an elliptical room that was actually the House of Representatives, or it's just outside the House of Representatives, from the very first Capitol building in Philly. And the reason that that's kind of cool is because John Quincy Adams, one of the founding fathers of this country, figured out that if he put his desk at one of the foci, so he always sat at a foci in this elliptical room. And the reason he sat there was because he could hear the opposition party were standing at the other foci. He could hear every word that they're saying. Okay? Because of the way that the sound waves bounce off.
Have you ever been to the Gustavus Adolphus? You stand in like the middle and you can hear yourself like.
Yep. Or there's in St. Paul they have at the Science Museum they have an elliptical room and you can stand at the focus and no matter what's going on also in the room you could. So if you're at one focus and I'm at the other focus and there's a rock concert going on around us, okay, we can sit there and we can talk at this level.
That's so weird.
Yeah, and we can hear one another and stuff. Yeah, it's pretty cool. It's an acoustical phenomenon in the elliptical room. So, a bunch of real-world examples there of ellipses. Okay? All right. So, this is the equation of an ellipse. How do I know it's the equation of an ellipse? Well, both variables are squared. Okay? That's how I know it's not a parabola. Okay? Because in a parabola, only one variable is squared. Both variables here are squared, so that makes it a circle or an ellipse. Second condition that I have to look at then is the denominators are different. So the denominators are the same, it's a circle. Denominators are different, it's an ellipse. Okay? So this is an ellipse because we have an addition sign in between the squared ones. Next week we'll talk about hyperbolas, and they'll have a subtraction sign in between them. Okay? So, that's an ellipse. What do you think the very first thing, I want to graph this one, by the way. This is the first one that I want to graph today. Okay? What is the very first thing that we should do with this ellipse? What do you think? Sam?
Maybe try to get the same denominator? Or does it not matter?
Can't get the same denominator. I mean, we could, but then it wouldn't be equal to 1. Okay. Think back to your prior knowledge.
Does it have a vertex?
It doesn't have a vertex. Parabolas have vertex. Or a parabola has a vertex. Okay? Circles have a... What do circles have? No? A what? A center. Okay, so circles have a center. So since this is like a circle, what do you think the first thing we should do is? Find the center point, because that's going to be our starting point. Okay? So the very first thing that we should do, step number 1, if you will, is we should identify the center of our ellipse. And we're going to do that just like we did with circles. Where is the center of this ellipse?
3, -2.
How did you come up with 3, -2?
I looked at H, K.
Okay. And
Did the opposite of the parentheses.
thought opposite because they're both inside a set of parentheses, right? Okay. So the center of this ellipse is located at the point 3, -2. Okay, so that hasn't changed. Inside parentheses, we think opposite. Okay, -3, think opposite is +3. +2, think opposite, -2. Okay? So step number 1, done. Found the center. So I'm going to plot that point or graph that point on my graph. And I'm going to put it on my graph with a C. If you put it on with a point, that's fine. It's not going to hurt you. Okay? It's not going to, I'm not going to take points away or anything like that. Okay? I just put it on with a C because technically it's not part of the actual ellipse. Okay? It's just it's the center. Okay? Step number 2 says, now what I'm going to do is I am going to look underneath the x squared term. So here is my x squared term. I look underneath it, and here I find the number 9. Okay? I'm going to take the square root of that number. So what's the square root of 9? 3. Okay? And that is going to be the endpoints of an axis, the horizontal axis. So the endpoints of the horizontal axis are going to be 3 units to the left of my center and 3 units to the right of my center. So I count 1, 2, and 3. 1, 2, and 3. And I put a dot at those. Now what I should do is I should erase these other dots so we don't get confused with those. Okay. That is step number 2. So let me bring you up to speed, or back to speed here as we switch slides. There is my center, 1, 2, and 3. 1, 2, and 3. There are the endpoints of my horizontal axes. Okay. Now, what I do in step number 3 is now I look underneath the y squared term, and there I find a 16. Again, I repeat that process. I take the square root of 16. What's the square root of 16? 4. Okay. But this time, because now it's underneath y, instead of going left and right, I'm going to go up and down. Okay, so I'm going to go up 4, 1, 2, 3, and 4. Down 4, 1, 2, 3, and 4. Okay. That gives me the endpoints, bless you twice, by the way. That gives me the endpoints of my vertical axes. Now, there are 2 axes in an ellipse. There's a horizontal axis and there's a vertical axis. One of them is called the major axis. The major axis is the longer of the 2. In this particular case, which axis is longer? The horizontal or the vertical? The vertical one. So the major axis is the longer one, which in this case is the vertical one. Which means then that the minor axis is the shorter of the 2. And in this case, it is the horizontal axis. Okay? Major is the longer one. Sometimes it's vertical, sometimes it's horizontal. Okay? Just from the equation, can you tell which one's going to be, now that you know how to get those endpoints, can you tell which one is going to be major and which one's going to be minor just from the equation? Yay or nay? Yeah? How do you think, Sylvia?
16 and 9, you can kind of tell, like, 16 will hold y because y is vertical,
Because 16 is under y. But how could I tell that the vertical axis from the equation is going to be the major axis? Okay.
Isn't it because 16 would have a greater square root than 9?
Because why? Because it's bigger. 16's bigger, so whichever denominator is bigger, that's which one's the major axis. Okay? So in this case it's y because 16 was underneath y. Okay? Okay? So you're looking for whichever bigger number is, that's your major axis. Okay? Step 4 says, excuse me, this is now the framework of our ellipse, so we are able to draw that ellipse in with us. Now again, it's not a diamond. Okay? There's curve to it. Okay? So take some time, piece by piece, little by little. Maybe you have to erase a little bit. There was only one, I think, when I was correcting tests last night, I think I only saw one pretty close to a diamond circle. Okay. But that is then our ellipse. Okay. Two more parts that we have to add to our ellipse. Okay. First off, let me get my ellipse back here now. So we had a center right there. We had endpoints right there and right there. We had endpoints right there and 2 and 4 right there. We had it look like that. Okay. Two more things. Okay. The last thing we need is, actually it's not the last thing, it's the second to last thing, but I changed that up. I forgot to add second there. The second to last thing we need are the foci. Okay. Foci, again, is the plural of focus. They are on the major axes. Okay. The foci are always on the major axes. So in this case, the foci would be up and down from the center. Okay. The most important formula that we have for the foci is c squared is equal to the absolute value of a squared minus b squared. A squared is always the number underneath the x term. B squared is always the number underneath the y squared term. So therefore, that's why it's the absolute value. Because in this case, 9 minus 16 is negative 7. So we have to absolute value that to make it nice and pretty. Other math teachers will tell you that a squared is always the bigger number and b squared is always the smaller number. Okay? But I found that too confusing, so I just make it a squared is underneath x, b squared is underneath y, and then it stays consistent. Okay? C, then, is the distance from the center to the foci. So I need to take the square root of that. So in this case, it's c squared is equal to 9 minus 16. So c squared is equal to the absolute value of negative 7. So c squared then is 7. So c, that makes c be the square root of 7. Now, square root of 7, I'm just going to leave it as the square root of 7. Okay? Or if it was the square root of 8, I'd simplify it to be 2 square roots of 2. Okay? Simplified radicals here. Now, since our major axis was vertical, that means we're going to add and subtract c to the y part of the center. So the two foci are located at the points 3, comma, -2 plus the square root of 7, and 3, comma, -2 minus the square root of 7. Okay? Because the major axis was vertical, I add and subtract it to the y. If my major axis is horizontal, I add and subtract c to the horizontal. Okay? So that puts my foci 1, 2, 3. So a little bit less than 3, so it puts 1 right there. And 1, 2, a little bit less than 3, puts 1 right there. It's a bad F. Okay?
Wait, where are you adding and subtracting? Or what were you talking about there?
C, my C value is the square root of 7, right? Which is a little bit less than 3. Okay? And I add and subtract that to the center. And I go along the major axis. So in this case, major axis was vertical, so I went up and I went down. Okay? So this one up here would be 3, comma, -2 plus the square root of 7. And this one down here would be 3, comma, -2 minus the square root of 7. And very, very, very lastly, the last thing we have are an ellipse has not 1, but 2 vertexes, so we call them vertices. And the vertices of an ellipse are the endpoints of the major axes. So in this case, the two vertices would be here at the point 3, comma 2, and here at the point 3, comma, -6. Okay. So if we were still having a quiz this week, that would be the question that I would ask. I would ask for the center, I would ask for the foci, and I would ask for the vertices. And I'd ask for the graph. Okay? What I'd like you to do now, or actually let's take a moment here to bring those all into one page, because this is what should go on your note sheet then, because we get to use that note sheet on all things. Okay? So first step, we're going to find our center. We've been finding those for a while. Second step, we're going to look under our x squared. We're going to take the square root of that, and that is going to be left and right from the center. Step 3, we're going to look under the y squared. We're going to take the square root of that, and that is going to be up and down from the center. The longer one of the two is going to be the major axes. The shorter one of the two is going to be the minor axes. Fourth step, we're going to draw our ellipse in. Fifth step, we're going to find the foci. And the foci will be on the major axes. And what we need for that is c squared is equal to a squared minus b squared, or c squared equals the absolute value of a squared minus b squared. That's going to give me c, and then I'm going to add and subtract it to x or y, depending upon which one is my major axes. And then lastly, my vertices are the end points of the major axes. Okay. Plenty of time. Save. Let's graph this one. Okay. Step number 1. Anybody?
Find the center.
Okay, where's the center?
1, -2.
Thinking opposite on both. 1, -2 gives me my center. Love it. Step number 2.
Look over the x squared.
Okay.
Take the square root and that's the endpoints left and right.
Okay. So square root of 25 is 5. So I'm going to go left and right 5, right? Does that tell me anything else? That gives me the vertices, because is that the major axes? Yeah, because 25 is bigger than 4, so this one is the major axes. Okay. Step 3.
Do the same thing with the 4.
Okay, square root of 4 is
2.
2, so that means I'm going to go up and down 2, right, from my center. That allows me to draw it in. Step 5. C squared is going to equal what? 25 minus 4. Absolute value, even though we really don't need it. Okay, what is 25 minus 4? That's going to be 21. So C is going to equal the square root of 21. Yes? Okay. So where are my 2 foci? Major axes is which way? Horizontal. Okay. So is horizontal x's or is that y's? X's. So I'm going to add and subtract the square root of 21 to my x's. So my center is 1 comma negative 2. So my foci are at 1 plus or minus the square root of 21 comma negative 2. Step 6. Step 6. Vertices. Vertices are what again? In words? Endpoint of the major axes. So what are the two endpoints of the major axes? That's everything that you need to know about an ellipse. Right there. Okay. Your homework this evening is going to be the front side of this worksheet that I'm going to hand out to you. Again, you have a formative assessment tomorrow in the Resource Center.
Is it just on what we just learned today?
It's on everything in Chapter 9. Everything's eligible. Yep. Because we're gonna work cyclical. But yeah, there will probably be a graphing and ellipse problem on there. Okay? And then on Wednesday, we'll do a quick spot check of the front side of this worksheet again.